Alright, welcome to another AQA A-level chemistry video. We've now finished organic year 2, and now I'm going to be starting physical year 2 now. And the first topic is going to be Born-Haber Cycle. Now, I did say in my last video that I was going to do exam questions as soon as I finished organic year 2, and I have got them coming up. So, but I'm just going to do it in the meantime of me getting those videos done for you. I will be uploading physical year 2 in the meantime. So, Born-Haber Cycle, right? Now this is quite a big, I think it's gonna be quite, I'm gonna expand on this in other videos, but this is quite a big topic for year 2 physical chemistry, because it's something it's gonna help you to answer questions. It's not like a difficult question, it's actually quite easy to do, and it's, I'll just say, a fun way of doing it. But there's like the cycle that you can draw out, which is the Born-Haber cycle. I think it's a really fun way of doing it, because like it makes it much easier for you to answer questions, and it's a way to easily get away with how to actually answer enthalpy, all the different types of enthalpy. Sorry about this. How to turn that one off? You guys know me. But I'll stop rambling on this. But I think it's quite a good topic to have a good foundation of, because once you know how to answer this, do the Born-Haber cycle, it can really help you kind of get to grips with all the other enthalpies of formation, and it is really just a very big. Think of a massive Hess cycle. It's kind of similar to the Hess cycle in the sense of like how you're drawing the root of your reaction. But when you learn about all the different types of enthalpy, and there are quite a few different types of enthalpies, this is a much better way of doing it than just kind of seeing where do I add, where do I minus. So when you're doing calculations, I advise doing Born-Haber cycle, and when I do finish all of physical chemistry, I'll do exam questions and you're able to see how I do them using Born-Haber cycle. But enough of me talking, I'm going to go straight into it. So the first type of enthalpy that you should know about is called lattice enthalpy. So there's two types of lattice enthalpy. So lattice enthalpy can be defined in two ways. Lattice formation, which is just the lattice enthalpy is the enthalpy change when 1 mole of a perfect crystal is formed from its gaseous ions. And then lattice dissociation is when lattice enthalpy is the enthalpy change when 1 mole of a crystal dissociates into its gaseous ions. So hopefully you need to know some. By the way, for these lattices, you need to know the definitions of these of these enthalpies. You need to know the definitions of these enthalpies. So I'll come through like a load of them, but you need to know these off by heart. So enthalpy of lattice formation is the lattice enthalpy. It's the enthalpy change when 1 mole of a perfect crystal is formed from its gaseous ions. And lattice dissociation is the enthalpy change when 1 mole of a crystal dissociates into its gaseous ions. Now here is an example of sodium chloride, or as you can know it as table salt. So this is a perfect crystal of it, right? Where I have the strong ionic bonds seen here. Strong ionic bonds between the oppositely charged ions, Na plus and Cl minus. Na plus being a much larger ion, cation, and being a much larger cation, and Cl minus being a much smaller anion. Lattice people get confused between say that lattice. I think initially people get confused and think that if I was to say I broke that bond there, right? Say I just broke this bond here in the background here, right? That would be lattice dissociation. No, that's not lattice dissociation. That's dissociating one bond, right? I'm gonna bring that bond back. But to be lattice dissociation is when 1 mole of a crystal. So this let's say this is 1 mole of a crystal, right? Say this whole thing is 1 mole of a crystal. Lattice dissociation is to break down all the bonds. It's breaking down all the bonds here into its gaseous ions. That's full lattice dissociation. Otherwise, if you're just breaking one bond, that's just that would just be bond dissociation, or you're just breaking a single. But lattice dissociation is breaking all the bonds within this crystal here. And then likewise for lattice formation, if you're just forming one bond, right? So if I was to I'm gonna remove this here, right? If I was to break that bond here, right, again, or if you see on the top right, and then I also do reform it again, that in itself isn't lattice formation. That's just bond formation, as simple bond formation, forming. And like I said before with other ones, but vice versa, right? If I was to, lattice formation will be the the enthalpy change required to form all of these bonds. And as you can see here, as it may turn out, lattice formation should be the exact same, is the exact opposite of lattice dissociation in terms of the fact that of what it actually is, but also in terms of the calculation. So let's say for to break all of these bonds, what I mean by this, right? So we know that bond forming is an exothermic process. Energy is released when bonds are being formed. So let's say the enthalpy of lattice formation, that's how you represent it. Use that. Let's say that's minus 1,018 kilojoules per mole. Now, what I mean that is exactly the exact opposite in terms of lattice formation and lattice association are exactly opposite from one another. Is that, of course, what they actually mean? One is completely destroying bonds, one is completely forming bonds, and then that's one thing. But also, the actual units require, the actual like values will be exactly opposite in itself. So the energy released from forming these bonds is minus 1,018 kilojoules per mole, but in lattice, enthalpy of lattice dissociation will be positive 1,018. So it takes 1,018 kilojoules. Remember, bond breaking is a endothermic process. Energy needs to go in to break bonds. So then lattice association would be positive 1,018 kilojoules per mole. I say this only because when you're doing a question, they may only give you lattice formation, and you need both lattice formation and lattice dissociation, or maybe you don't need lattice formation, you need lattice dissociation. And if they don't give you, if you go into exam and you say, oh, I need the lattice association to answer this question, because the lattice association is actually part of another equation that I'll go on to later on in another video when we're doing enthalpy of solution. But if they give you lattice formation, don't think to yourself, I don't have enough information to answer this question. Think to yourself, if lattice formation is the exact opposite of lattice dissociation, right, and they give me the lattice formation, it's minus 1,018 kilojoules per mole, I can now assume, now they won't be exactly, experimentally not exactly going to be 1,080, but for AQA A-level chemistry, you can make the assumption of saying in perfect conditions that the lattice formation is the complete opposite of lattice dissociation. So they give you the lattice formation in your exam and you need lattice dissociation, and they say lattice formation is minus 1,018 kilojoules per mole, then you can just say lattice dissociation is positive 1,018 kilojoules per mole, and then use that to answer the rest of your question. I'll move on from that now. Hopefully that made sense to you. Enthalpy of formation. So the enthalpy of formation is the enthalpy change when 1 mole of a substance is produced from its elements in their standard state. Now don't confuse the enthalpy of formation with enthalpy of lattice formation. That's completely different. Enthalpy of lattice formation is enthalpy change when 1 mole of a perfect crystal is formed from its gaseous ions. And so here, see here, this part here is that similar to lattice formation, but what isn't similar is this part here. So we're actually forming them from. Lattice, enthalpy of lattice formation, we're forming this perfect crystal lattice from specifically gaseous ions. Oh, I don't like doing that. Specifically gaseous ions. Whereas enthalpy of formation is the enthalpy change when we're forming a crystal from their elements in their standard states. So for example, if we're forming CO2, if it was enthalpy, and not to say that CO2 is an example of a crystal lattice, it obviously isn't, but say it was, right, just say example if it was, right, if it was enthalpy of lattice formation of CO2, both carbon and oxygen would need to be what's it called? They would both need to be gaseous ions. So you need to form an ion of carbon, which obviously would never happen. But I'm just saying experimentally here. Again, this would never happen, but just to show you my example here, like if it was enthalpy of lattice formation of a carbon dioxide, you need to have an ion of why did it do that? That's weird. You need to have an ion of carbon of some sorts, and then a gaseous ion of oxygen, which is that is possible, but again, I'm just doing this experimentally here, right? We'd form a gaseous ion of oxygen, I guess you could have C plus, and a gaseous ion of carbon, and then you can do lattice formation to form the crystal, right? Whereas lattice of formation is not that. So enthalpy of less of formation. Sorry, enthalpy of formation is not the same as that. That's why you'd have to go start saying we can just form carbon as it is. So carbon in its element at its standard state is just carbon solid, and oxygen in its standard state is oxygen, but it's also diatomic. It's not separate. So it's just in a standard state, it's O2 gas. So from enthalpy of formation is just going from their standard states as they are under standard conditions straight into CO2 here, right? That's the difference between enthalpy of formation. You can just be from whatever state that they are naturally in into the compound that we want to form at the end. Now I say this because this whole thing here about this is kind of like the enthalpy of formation is like skipping all the steps of different types of formation. So all these formations I have here, lattice enthalpy, I'll go into all the types of enthalpies: ionization energy, MPL atomization, bond enthalpy, electron affinity, all of that, right? They all can be added up. That this is what's happening during formation. So when you're actually undergoing enthalpy of formation, what's actually going on is all these different enthalpies in stages. So all of these different reactions, enthalpy of formation, we're tricked into this idea from GCSE that from what you understand is that enthalpy, all these reactions will go in one step. From GCSE, you understand that if it's just one, this perfect example here, if you have sodium solid, right, and then chlorine plus CO2 gas, right, you just form instantly, obviously you balance this out here, right, 2 NaCl. Now that isn't what's actually happening in reality. It doesn't just go in one reaction. This is what enthalpy of formation would be. Just the straight equation that you know. Na solid plus CO2 goes from 2 NaCl. That is what enthalpy of formation, what you're used to. In reality, there's a load of sub steps that actually happen to get from this stage here. I'll change color. To go from this stage here to get to eventually here requires quite a few number of steps, and I'll go through them. But lattice of formation was enthalpy of formation is just one of the steps. So, and that's usually actually at the end. This is one of the end steps actually. So I should have put that at the end. But yeah, this is just one of the end steps, and I'll go through the BornHaber cycle at the end, so you can clearly see where all the steps are. So don't worry about. I need to know which steps are. I need to note down where. So there'll be a diagram at the end, which is the BornHaber cycle, which shows you which steps happen at which point and helps you understand the route at which they actually occur at. And over time, when you do many of these questions, as I said before in many videos, if you want to know how to answer questions well, the best way of doing that is by doing past paper questions. But when you actually answer these questions, you get to realize by yourself, you don't have to actually look at the cycle and memorize the cycle, how these reactions actually happen. They all end in lattice formation. If I'm forming something, they all end in lattice formation. If I'm trying to break a crystal down, they all start with lattice dissociation. And if I'm trying to start from something, if I'm trying to start a reaction, I may have to think about ionization, atomization, ionization enthalpies. I'll go through those later in the video. But it's just about understanding what routes that we take to actually get to forming our compound, and all of that together, all of those enthalpies together. Some of them are negative because they're exothermic, and some of them are positive because they're endothermic. Now, majority wise, it should be exothermic because bond forming is exothermic process if we're talking about bond forming, but there are examples where it can be positive. But overall, once you've added all those different enthalpies up together, the enthalpy of formation is the sum of all those different enthalpies together. So it will be the endothermic reactions plus the exothermic reactions. So we'll be taking away some, and then that's how we work out overall enthalpy of formation. And when you do the exam, they may give you the enthalpy of formation and they want you to work out enthalpy of ionization or anything like that, and it's just literally about using simple math or simple algebra. But yeah, that's kind of, I kind of went a bit off with enthalpy of formation, but that is what you need to kind of get a grip with. Hopefully that made sense. All right, so this is obviously ionic bond here, showing the attraction between the ions. And the ionization energy, right? So you should be familiar with ionization energy from either physical, I think physical year one. Yeah, surely from physical year one. Right? I have talked about ionization energy, but I'll say it again. Now, the ionization energy is the energy change when 1 mole of a gaseous atom loses 1 mole of electrons to form 1 mole of gaseous ions under standard conditions. Now, I've got a this little diagram here to kind of give you an understanding of what I was talking about before about the steps, right? Because you need to, that is all you're doing here. As I said before, you're taught from a very young age. I don't say from a very young age, but you're taught from generally from GCSEs that all these reactions happen in one step. And I mean, you obviously know not, but you don't understand how the steps actually happen. And I'm gonna just break through. Even this is quite a very simple understanding of the steps, but for A level, kind of getting grips of this would be enough. And obviously, I'll go through the Born-Haber cycle later on. But say we start over here, right? Oh, I forget you can't see my I forget you can't see my hand gestures. Usually you can see my hand gestures when I'm actually explaining this. Yeah. But anyway, I'll use my pen. Yeah. Actually, I use a different color, right? I said pick a different color. I pick the same color. So here's, let's say this is the start of our reaction, right? So this start, not what I wanted. There you go. Start of our reaction here with the metals and the non-metals, right? So that's how they are. So metals would be solid. Most metals, of course, excluding mercury, and weak metals like gallium and all that. But let's say this is a start of a reaction of the metals, non-metals, and we wanted to get to the point here. This is the end point of our reaction, right? This is the end point of our reaction. How do we get from here to here? Now, first of all, we have to think about we would have to think about how do you actually break down a compound. So we need to isolate the atoms. So if we want to isolate metals, we're going from basically a solid into liquid. Wouldn't be enough. That's not isolated. We need to form gases. Now for metals would be subliming. Sublimination is pretty much going from a metal stage, so from a solid stage into a gas. Yes, I believe so. Yes. If I'm wrong on that, if I'm wrong on it, I'll edit it in, at the end, or leave a comment at the end of the video saying, or in the description saying what sublimation is. I'll probably leave the definition of sublimation in the description. I forgot to mention. I'm pretty sure sublimation is going from a solid to a gas. But if in case I'm wrong, just double check that one. But I'm pretty sure that's what it is. For non-metals, lattice dissociation, entropy of lattice dissociation, that would be the dissociation of these. Because remember, if we have the example here is as shown from before, sodium chloride. So these are still gas, but we need to break this diatomic bond. So you need to break this covalent bond between the diatomic atomic bond. See, this covalent bond. It's actually atomic bond. Sorry, it's covalent bond between the Cl atoms, because that we need to isolate the atoms by themselves, and this is technically a part of something called atomization. That is this is the next part here, just underneath atomization here, but yeah. So this process of metals being broken down into gas, so subliming them into the gas, and that's association here. All we're trying to do is something called entropy of atomization, where we're just trying to separate the atom by itself, because CO2 is not atomized. That's actually although it's in the gas phase, but it looks by itself, it's still two chloride atoms. Atomization would be 2Cl gas, which is possible. It requires energy to break those bonds, but it's possible. Then from then on, we would get we would have sodium gas metal, or by itself after atomization, and then we would also have Cl gas metal. Now, that's fine. This is okay. This is where we want to be, right? This is the first step of what we're trying to do. So this process here is just of atomization, right? It's for both of them actually issues. That's a terrible. All right, so we've atomized our, or formed atoms, or separate atoms, our isolated atoms, I should say, of sodium and chlorine here. But they can't react. You know, by themselves, that's quite difficult. Requires a lot of energy just to get used to react by themselves, right? So what we need to do now is we need to form ions. We need to form ions. We need to form Na. And when we know the ions that we know are Na plus and Cl minus. Now, how are we going to do that? If we're going to get Na plus, we need to do ionization. Now, ionization, as I said before, the enthalpy change when 1 mole of gaseous atoms loses a mole of electrons to form 1 mole of gaseous ions. And in this case, the first ionization energy will be the enthalpy required to lose 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of unipositive ions. Unipositive meaning 1. So forming a mole of gaseous Na plus cations, or I use or forming a mole of gaseous unipositive cations, Na plus cations here, from removing 1 mole of electrons from 1 mole of sodium atoms. Yeah, let's say these here, right? And then with chlorine, we have to do something called electron affinity. And now electron affinity is kind of the opposite of ionization in terms of the fact that it's the energy required. It's opposite in what it's intended to be. It's not opposite in terms of in terms of values. Electron affinity and ionization are not always it's probably like one or a couple of examples, but they're not the same in terms of value. So if ionization is one value, let's say if you're removing an electron, to remove an electron requires energy. So that's, say, it depends on the situation. Really. Again, depends on the situation, but ionization, to remove an electron, generally requires a lot of energy. So let's say plus 67 kilojoules per mole. If you was to add that electron back on an atom, it's not necessarily plus 67 kilojoules per mole. It's more complex, but you don't need to know about that. You don't need to explain. You don't need to explain why and assume why. But I'm just saying it's not the same thing. Lattice formation and lattice association, fine, but don't assume that same thing with electron affinity. I just wanted to say that they're opposite in terms of what they're doing, because ionization, you're removing 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of unipositive ions. Now with chlorine ions, you are forming unipositive ions, but you're gaining, or you're adding 1 mole of electrons to 1 mole of gaseous atoms to form 1 mole of unipositive chlorine atoms. But these are anions, not cations. So again, we're giving chlorine a 1 mole of we're giving chlorine the chlorine gas, or chlorine atoms here, the atomized gas, right? 1 mole of electrons. They're gaining 1 mole electrons to form. Sorry, we're gaining 1 mole of electrons. To. So yeah, I need to make sure that I don't say this in the wrong way. Electron affinity is when you're forming 1 mole of gaseous unipositive ions from adding 1 mole of electrons to 1 mole of gaseous atoms, right? So we're forming Cl minus here. Now these two can react. These are isolated atoms. They can now form, and they can now start going lattice formation. This can now undergo lattice formation, and then I don't like using that in these two can react, and now they can undergo lattice formation. It's enthalpy of lattice formation. I don't know, it's LE here, but enthalpy of lattice formation. And now we've formed sodium chloride crystal solid, like I showed you up here. So this is just meant to be this is just meant to be an example of this. This is a 3D compound, 3D structure, of course. All right. Enthalpy of atomization, as I said before, is the enthalpy of atomization is the enthalpy change when 1 mole of gaseous atoms is formed from its elements in its standard state. right? So enthalpy of atomization is enthalpy change when 1 mole of gaseous atoms is formed from its elements in a standard state. So if we have H2 gas, enthalpy of atomization would be, because H2 is a gas in its standard state, to go to form hydrogen, one single hydrogen atom as a gas. That's atomization. But carbon solids also, no, so let's say, yeah, carbon solid turn into carbon gas. Carbon in its standard state is solid. For trying to think of an example of atomization. I mean, it's just about just getting any element from a standard state and then forming it into a singular atom in the gaseous form. That's all that atomization is all about. So any atom, it's a CO2, H2. If it's diatomic, make sure that it's a single atom and it's gaseous. Uh, Sorry, had a bit of a problem there. No problem now. Electron bond enthalpy, right? So the bond enthalpy is the average enthalpy change on one formation. Sorry, sorry, let me say it again. The bond enthalpy is the average enthalpy change on formation of a mole of identical bonds in the gas phase. The average potential. So bond enthalpy, this is the one that you guys all know, but this all it is the average potential chemical energy stored within a bond after formation. I say this because I think I did explain this when I was going on that video, on a previous video. I won't remember the video that I said it on, but it is pretty much that. For example, for CH4, if you have methane, right, the bond enthalpy for a carbon hydrogen bond isn't the constant throughout every single bond dissociation. That's because when you break a carbon hydrogen bond on let's say here, right? Now, not all, I know this is a bit short here, I should like that, right? But if I was to break this bond here, I remove this carbon hydrogen. Oh, damn it. I remove that. I don't like doing that. Okay. Why does it keep doing that? Let's use this one here. So I remove that one there, right? Now, say that would use up a certain amount of energy to break that bond. Now, the electrons have the carbon atom has a is more positively charged because now it's the one less bonding pair of electrons that's trying to bind to. So now, because it's more positively charged, the bonding pairs here are more attracted towards the carbon, and so they move like this towards the carbon here, towards the carbon here, towards the carbon, and therefore the bond becomes much more stronger. If I keep on removing electrons, it becomes more positively charged. The electrons in the bonding pairs move much. I don't like you doing that. Move much closer towards it, and therefore eventually, if I was to remove the last one here, the more that I remove, the more carbon hydrogen I remove, the stronger the carbon hydrogen bond becomes, right? The stronger that carbon hydrogen bond becomes, and therefore it's not constant. The carbon hydrogen bond isn't constant throughout. Now what we measure we measure the average potential energy. So if I was to measure all these carbon hydrogen bonds, or if I was to break all of the bond, the potential energy stored within those bonds, I measure the average energy of all those bonds together once they form. So if I get those bonds back, right, the average bond enthalpy, or the bond enthalpy, is the average enthalpy change on formation of a mole of identical bonds in the gas phase. Now, I only say this, I remember, I only try to tell you things that are actually relevant to your exam. I know sometimes maybe I kind of go a little bit off topic, but I try to go things that are relevant to you in your exam. The reason for this is because they may ask you a question and say, why is so if the experimental value may be different to the textbook value. And I was saying that the experimental value is the actual bond enthalpies of your example, so if you get, so your, when you actually do your, they'll give you the bond enthalpy or the bond enthalpy of formation for the experimental value. So when the experimental value is someone actually doing the experiment, whereas the theoretical value is getting it from a textbook and saying, if I was to do the average, but the bond, the enthalpy of formation for this type of reaction what would the overall formation be, or how much energy would it require if I was talking theoretically under perfect conditions or whatever. Now the nth bill, and they'll show you two of them, and it'll be slightly different. It's your responsibility to say the reason why. They'll ask you questions saying why are they different. Say the reason is why is that one is an experimental value, one's a theoretical value. The experimental value uses the actual bond enthalpies, whereas the theoretical bond enthalpy uses average bond enthalpies, which is not the same as the actual bond enthalpies for all of your reactions. And so that's why you can get different values, and that's why I say, because they try and compare the two, and it's your responsibility to say that the reason why this is different is because, as I said before, then you have to go, and you say it on your point. So experimental value is the actual bond enthalpies, whereas the theoretical is average bond enthalpies from a textbook. That's why they're different. All right, let's go continue now. Electron affinities. Electron affinities enthalpy change when 1 mole of electrons is added to 1 mole of gaseous atoms to form 1 mole of sorry, one sec. Sorry. The electron affinity is the enthalpy change when 1 mole of electrons is added to 1 mole of gaseous atoms to form 1 mole of gaseous ions. Like I said before, it's just the opposite of ionization in terms of what's happening. It's enthalpy change when 1 mole of electrons is added or gained to 1 mole of gaseous atoms to form 1 mole of gaseous ions, and this would be considered the first electron affinity. So enthalpy change with gaining a mole of electrons to 1 mole of gaseous ions to form 1 mole of uni-negative gaseous ions. All right. Now I'm coming up to the final part of it. I know you're probably tired of me speaking, so I'll try and get straight onto the point here of the Haber cycle, what the Born-Haber cycle is. Now, the Born-Haber cycle can be used to calculate some of the types of enthalpy change from experimental data. Born-Haber cycle. So you can break down an ionic reaction into a series of steps. You turn the pure elements into gaseous atoms. Then you form the ions via electron ionization and affinity. Then you condense the gaseous ions into a crystal, and you can then use this principle to generate Born-Haber cycle. So this is literally the steps. This is how you, over time, you don't have to learn this. Over time, you'll just realize that this is how the steps of most of these reactions happen. From the natural states. If I want to form an ionic crystal from the natural state, I have to think about this, right? So I have to get the actual atoms, and I have to form to pure elements into, so pure, I have to form in, sorry, I'm getting ahead of myself here. If I was to get from my standard state elements to pure to a crystal, ionic crystal, how do I get to that point there? And it's because you have to turn the pure elements, you have to get your standard states, right, your standard state elements, and turn them into pure elements, into gaseous atoms. And then when you have that, as you said before, you've done your atomization, which is that this is basically atomization, right? You then need to go to some sort of ionization process, so electron affinity, enthalpy of ionization to form ions. Once you have those ions, you then need to go, by electron ionization or affinity, you then need to condense the gaseous ions into a crystal. So once you have your ions, you can then do lattice formation to form the crystal. And all of that is the principal generator for the Born-Haber cycle. So before I kind of get onto too much, I'm gonna show you what Born-Haber cycle looks like. Now, if you know the example of the Hess cycle, I don't know if I've gone to Hess cycle. I think that's coming up more in year 2. No, I definitely done a Hess cycle before. Yeah, it's year 1 content doing Hess cycle, but remember the Hess cycle was looking like this triangle here to there. So A plus B there, B plus, so it goes B plus C or something like that. And, I was doing this example here, and you can kind of see what was going on here, right? This is a terrible example of what I've completely forgotten what the units would have been after the arrows, but I know you guys probably know what it looks like. It looks like something like this, right? It looks like something along the lines of this. Now this is kind of like, that's a very basic way of thinking about your reaction. If you don't have a lot that is going on, whereas for this Born-Haber cycle is a much better way of I say a much better way, but it's a more easier way to show off your what you understand from the practical. In terms of, you can now clearly see here what's going on. I like doing this because I can see when I'm doing the slanted arrows going from positive to negative, I can maybe get a bit confused. So I don't like kind of doing the hair cycle. But hair cycle, they may ask you to draw hair cycle, so you should know what a hair cycle is. But the Born-Haber cycle, I'm literally just going up, showing the positive values going upwards and the negative values going downwards. In terms of now, this is how a reaction is actually happening. So we start off with our the start of our reaction is just the elements of the pure states here. And then we have, I said we're literally following this step as we're going, right? So our first step would be here. We need to form our pure elements. Now you have to break down each step one by one, whereas hair cycle kind of just goes for all steps in one arrow. Now all steps one by one would be, first let's do the atomization of just bromine here, half Br2, right? Half Br2 would be for atomization, that would be a certain amount of energy, and that's what we've done here. But we still haven't done the atomization of potassium yet. So that first step is just the atomization of just bromine. The second step would be atomization of potassium. Now we have that's our atomization done. Now what we need to do is enthalpy of, we need to now form ions, ionize our compound. So if we want to form an ion of potassium, we need to do enthalpy of ionization of potassium to form K plus here, and it will release one electron, and we have bromine here now. Now we also need to ionize our bromine, but bromine is extra electron affinity, but because bromine is actually quite electronegative, in this particular case, we just add it first electron affinity, we'd be actually losing energy because it's that you're giving the bromine is gaining an electron that it wants to gain. It wants to gain it. It has 7 electrons in its outermost shell, and it wants to form that last electron to fill its last shell. So this would be to go from Br to Br minus. It's electron affinity here. So I have our K plus, the electron that's lost from the potassium here can be used for can be gained by the bromine here. Now we have our ions. We now do lattice formation here, and that is the Born-Haber cycle, right? I want you to now, to get you familiar with this, I've actually got a question here for you. So I've given you all the types of enthalpies of form of enthalpies here I showed them above. Now what you want to do, I want you to work out the enthalpy of atomization of Br2. Right, so we're gonna give you examples. So take a note down these values here, pause the video, note down these values. And I want you to try and answer. So I've given you all of this apart from, I haven't given you enthalpy of formation of Br2. I want you to work out the enthalpy of formation of Br2 by pretty much giving you everything else. So try and do that. Alright. I've assumed you paused the video and you tried to answer that question. So I've given you all information. So we can actually work out. I just need to get my calculator. You will use your calculator when you're answering these types of questions. Let's go over the top because it's quite easy, right? So enthalpy of atomization of now, and I should also make this clear. So if they give you one, then you can just use it straight away, and they may ask you to draw it on next to it. But even if they don't give it to you, they're more likely to give you an example. They just give you a blank piece of paper and then just draw it out. How I would go about this is I like drawing the Born-Haber cycle. So in your exam, you can just go as, you don't get any negative marks from doing this, but how I actually answered the question when I'm doing they asked me to work out the enthalpy formation, and they've given me all the other information to answer this question. I just do this, say, okay, so enthalpy of atomization, that's there. You don't need to do the whole thing of, using a ruler and then doing all. You can just do, like, say, okay, enthalpy of atomization, that's that, and then write it down, that's X, whatever, and then enthalpy of the other atomization, I have to take that into account, that's Y, whatever. Also, I'm just saying, just using X and Y as examples here. I need to do ionization energy, fine, that's that, right? Oh, sorry. Formation, I know that's negative, so that's that. Oh, sorry. I'm not. You obviously don't need to do this. I'm just using examples. I'm not using specific examples. So you get values to represent these. Okay, lattice formation, that's negative. All right. So once I get here into I have to do electron affinity first. Then I do that formation there. All right, cool. and then you fill in the little gaps with your numbers in it. So it can be 91 or whatever, minus 91. And then once you have that, you say, okay, I've written down all the, I haven't even come to the question yet. Obviously read the question first, or if there's a lot of information, but you can say, I haven't even gone to the question yet, but I can see I've got the information here, 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 and I have, the only one I'm missing out on is, let's say I make up random, let's say I make up random values now. Okay, 45. This is meant to be, this is just random numbers here, right? It's minus 212, and then minus 313, right? So you can see here, right? So that we've got information for every single formation except for one, and now we can use simple maths to work out what this value for x is. Now that's what I'm trying to do here, right? I'm going to remove this little table here. I'm gonna remove that because that's just blocking away. I don't want to confuse people about what that is. Good. All right, so we have the enthalpy of, so if you already want to get to the answer, just skip to the end of this of if you already have your answer, just skip to the end of this if you got the right answer. But if you didn't get that, I can just show you how I went through it, and that's what I'm gonna go through here, right? So enthalpy of atomization of potassium, right? That's 89 here. Now be careful with the, if there's any halves in front of the molar ratio, the molar value, right? Now this is just potassium by itself. Atomization is just going to be as itself, but so you don't have to worry about that. But in terms of ionization NPs or electron affinities, if it's half a compound, you need to be wary of that whenever you're going through that. There is an example here, so keep in mind of that. But potassium is just 89 kilojoules per mole. That's fine. Ionization energy of first ionization of potassium is 419. So 419 here. So actually, I probably don't want to have it here, or don't have it. Yeah, 419 kilojoules per mole. This is per mole. Now you don't have to actually draw this in your you don't have to write this down, but you can just kind of note down your, you know how, you guys know, should know how to note by now, right? You should know how to note by now. You don't have to be so formal unless they specifically want you to write it in a specific area. But more time you're when you're actually writing it down, you're just writing it down to help you understand the question. They'll give you more than enough time to answer this question. So it's like probably 3 minutes, maybe 4 minutes. And it's more than enough time to go and answer this question. To do a little diagram. I prefer doing a diagram because it just helps me out. So 419, 89 here. Of electron affinity of Br, 324. It's 324.6, but in the exam it'll actually be written more like this, 325. They don't for electron affinity, all these entities they like to round it up. So this is minus 300, and electron affinity should be, sorry, this should be, my bad, sorry, this should be minus I forgot to write down minus 327, minus 325 here, right? Kilojoules per mole. Lattice formation of potassium bromide is minus 672. Minus 672 kilojoules per mole. Potassium bromide, so enthalpy of formation of potassium bromide is minus 494. Now we've got everything here. Now this is just X, right? Technically, what's the question says here? Work out the enthalpy of formation of Br2, not half Br2, Br2. Be careful because I've made this mistake in the past. Now, how I would write this out, I'd leave this as half X because I do maths. I like using like values like X, so minus 300, minus 494 here. Kilojoules per mole. Leave that as half X. Now, you can clearly see here, if you do simple algebra, if you ever had a shape, right, and you say the work out the value of x from a, this is a square, this is a rectangle technically, right, but because it's not exactly square, but say this is a rectangle, right, and it asks you to work out, in reality, right, you're doing actual enthalpies and working out, doing this plus this plus this, negative ice, but how, if you do it like this, you've now got a perfect example of an algebra question that you know how to do in maths. They said work out the distance between, let's say this is a square, right, or rectangle, whatever, and they ask you what's the difference between here to here, and they've given you here to here, right, and that entire side here makes it very easy to work out that side, right? So we just do, let's add these all together. So 419. So if I was working out. All right, so as I said, treat this by small technical difficulties. It's all good now. So yeah, so if I was to do this, like, so I'm think about, I'm treating this like a square, right? I know the whole of this side here is equal to the whole of this side here, but I'm just missing a little gap here, right? Because this side here is equal to this side, but I'm just trying to find this little gap here. So how distance between here to here. But how I'm gonna do that, right? So I make this side equal to that side. So I mean, there are different ways of doing things. Let's just say what we're doing here, right? So I'm taking away this side from this side. So sorry, taking away this side from this side. Sorry, make that make sense. So, enthalpy of. I'm gonna write. No, you don't always have to write this out. You can sometimes just make it easy to write out yourself. But in case you can't see it, I'm just gonna do it, right here. So, first I'm gonna think about how am I just gonna go do this, right? So, that from that. Yeah, I could just do that. So enthalpy of, or minus r enthalpy of lattice formation plus negative r enthalpy of electron affinity of bromine equals to enthalpy of formation of potassium bromide plus enthalpy, also in this case would be, yeah, enthalpy of what's negative here, sorry, that's a negative there, plus enthalpy of half the enthalpy of atomization plus the enthalpy of atomization of potassium plus enthalpy of ionization energy. Again, if you just want to go straight to the answer, go straight to the answer. If you want to skip this part out, then you can skip this part out. Don't worry about trying to state every single part of this. To be honest, I'm just not bothered to edit this part out. But as I said before, we know that side is that side. How can we make sure that we just get half the half x? Because all you really care about here is the half x. So get half x here, right? Isolate that part out. And that's just equal to this as it is. So activation energy of bromine, sorry, electron affinity of bromine minus, and we just keep this as it is, but we just haven't got the half x there. Kind of isolate that off part there. Hopefully this makes, this is probably a lot. But all I'm doing here is that I'm trying to do this, all of this, right? For the 672 plus 325 minus 419, 89, and 394. And that should equal what this half x is here, right? Therefore, half x is equal to, I've treated them all like positive because I'm trying to treat this like a square. And I've shown how here, because I've drawn this out because I've written this out because in case they say, oh, it's not you haven't explained what you mean by here, because usually you just do you'd use the minus for 672, but it might be a bit difficult. for you to grasp where it's actually been negative and adding. When you're doing it like this, it's very easy to see you can treat it like an algebra equation, right? That's why I've done it like this. So I've written out what I've just done here. So a minus make it positive, to show what I've done here, right? But all I'm doing here is 672, right? Plus, 672 plus 325 minus 394 plus 89 and 419, right? So that's 672 plus 325 here, 997 minus 300, so 394 plus 89 plus 419, 902. So half x is equal to 997 minus 902. 997 minus 902 is 95. That's equal to 95. So half x, so this is called how is half BR2 is equal to 95. Now, in this question, they asked you, usually they'd ask just for the enthalpy of atomization of bromine is, but the question that I asked you, what the enthalpy of atomization of BR2 is, not half BR2. That's the question that I've asked you here, BR2. So this wouldn't get you the 4 marks. If this is a 5-mark question, they would give you 4 marks to get into this one here. But just doing BR2 or x instead of half x, times that by 2, 190. Is that 190? Wait, let me just make up. 95. Yeah, just 190. 190. Hopefully my mental maths isn't failing on me. Wait, is that... If I've been really dumb? No, I'm not having dumb. 190. Mental maths is still there. And that's it. And it will be positive. Now, when you're doing this method, the reason why teachers that are looking at it say don't use this method because it can be quite misleading is because if you don't know what's going on here, I know that this value is positive because I've converted all of these values into a positive value to help me make it easier for me to take away the values I don't need. But say this was if I was trying to work out what this is here, what the enthalpy of formation is here, and I got a positive value because I changed everything to be positive, I'd say, okay, fine, I found the value, I finally got my answer, but the answer I'm working for is meant to be negative. All I do now is just flip the sign. But because I know this is a positive value, I can say, okay, cool, it's just here, it's positive 190 kilojoules per mole. But for if I was working out a value that was what was this what I was working out? I was atomization here, right? Atomization. But if I was working out a value that's negative here, all I do is just flip the sign. But that's literally it, to be honest. That's it. I know this has been a long video, but this is I'm trying to make sure you have everything you need. All the other videos will be less well, I say all the other videos, you know me, but the videos that I'll release next will be less lengthy. But I'm trying to give you every little bit of information when I'm going through this. So because this is the biggest topic in terms of as long as you understand this basic principle, you can then understand pretty much all of the rest of the topics. So I just want to make sure you get this basic principle done, and then for everything else, it can be calmly done. But yeah, so you'll be able to speed run for most of these parts of the video. So I just wanted to just highlight. I just wanted to summarize everything that's been put down here. So enthalpy changes. So lattice enthalpy. Yeah, I'll write it down as enthalpy of lattice. The different types of lattice enthalpy, right? Let's go over everything. Lattice. I'll just call it lattice enthalpy. And accent. I'll write lattice enthalpy because that could be formation or dissociation. So just knowing that the difference between the two, lattice dissociation and lattice formation. But lattice enthalpy in that case is more than fine. If you see LE, that just means lattice enthalpy, and it's just saying if your lattice enthalpy is positive, then you know it's it is formation, and if it's negative, so if it's positive, it's dissociation. If it's negative, it's formation. I already explained why. Enthalpy of formation, enthalpy of atomization, keep doing the capital T here, atomization, enthalpy of ionization, so enthalpy of ionization, bond enthalpy, and electron affinity. How do I represent bond enthalpy? I should say, well, I'll say enthalpy of electron affinity, fine. Bond enthalpy, just write down bond enthalpy, I don't know how to represent that. But that is it. That's the end of this video. Hopefully you didn't get too bored and you've actually, hopefully you skipped parts of this video. That's probably what I'll say. Hopefully you skipped part of this video. But yeah, that's it.